Okay, then I guess we can get started slowly for today. Welcome back to day 2 of the CIG Tectonics modeling tutorial. Before we start our day today, we wanted to explain to you a bit what CIG is and who funded this tutorial and who organized it, and Lorraine will say a few words about that.
I'm going to actually share my screen just for the fun of it. I'm going to try to share my screen. Okay. There we go. So yes, thank you everybody for joining us once again for day 2, especially for those who are in large, I'm going to call Delta T time zones. This really pleased us to see such a great demand for this tutorial. Again, I am Lorraine Wong. I am the director for CIG. Some of you may be new to CIG, so I thought I'd give you just a short introduction to who we are and what we do. So CIG, as you can see from my homepage, our mission is to develop and disseminate software for geophysics and related fields. So what this means is that as far as developing, means that we support code communities like Aspect and other community-driven software. We do this by sponsoring tutorials, hackathons, as well as supporting the direct support of code development. We do this through several mechanisms, and one of the mechanisms I want to make you aware of is we've started some postdoctoral opportunities. A new ad will be out in a couple of months for people who may be interested in contributing to community code development or bringing their own community code. We support, as I said, open source science and open source communities for the geosciences. Some other things I'd like to highlight besides our tutorials and modeling events, we also have webinars. Everything that we do, you can find on our homepage. As you see, currently there are no webinars scheduled for fall, but we do host a webinar series every year that aims to bring sort of new topics to geodynamics. This year we'll probably be joining the modeling collaboratory seduction zone effort, so stay tuned for that. Lastly, I want to point out from our homepage, you can get to any of our software stacks. If you're looking for other community software, you can see our software stack here. There's software that'll help you solve problems in short-term crustal dynamics, long-term tectonics, mantle convection, seismology, dynamos, and we have some just generic computational science software. All of these can be downloaded from CIG. The other thing that you should be aware of is the forum. We encourage everybody to sign up for our forum. Our forum is, we have a generic forum that's announcements. If you want to get stay abreast of everything that's happening with CIG and across the community, those get posted to the announcements forums. And there's also an Aspect forum as well. So if you have specific questions and you need help with Aspect, please go to the forum and post as well as help contribute to the Aspect community by answering questions that you can help along with. As most of open source software development is really community driven, and the more contributions that you can provide us, builds a more robust community. Anybody can join the forum and anybody can post to the forum. So please join and become part of the CIG community. We will be heading into planning this fall. We have one big event coming up, and that is the CIG community workshop. We haven't started registering for that, but we invite all of you who are here to attend and contribute to the planning to envision the next round of CIG, especially if you benefit from events like this. And this is very important for early career scientists to help us mold mold the direction for the future.
Okay, thanks so much. So this means we will now start with the lessons for the second day. And the schedule will be just like yesterday. We will start around now. The lessons will go until around 1 p.m. here, East Coast time. So that's 10 a.m. Pacific time. And whatever that means in all of the other time zones. And afterwards, we will have around a 1 hour discussion group. Yesterday, we had around 22 people there. We'll see how that develops over the week, depending on the more complex models that we are going to discuss. It might be more or it might be less. We'll see what we do today. And today I will be talking, and that means I will share my screen and show you what we are going to talk about today. So I wanted to start today's lessons by talking about the virtual machine that you are using, because today we are going to start using some more advanced models, and we will also do some compiling inside the virtual machine that can potentially take quite a lot of time. So before we start with the actual lesson, I wanted to make sure that most of you, or all of you, have configured the virtual machine to be as fast as possible for this week. So if you have already started your virtual machine, could you maybe shut it down again, just for the beginning, so that we can take a look into the settings? If you have a lot of windows open, then maybe you can also keep it open and look into the settings, or if you already adjusted the number of CPUs and the number of memory and you are comfortable that you just picked something that's good, then just keep it open. But if you want to take a look and see if you can improve that, then please shut down your virtual machine at the moment. And we will take a look in the settings. So this is my VirtualBox version. It will look different for you depending on your operating system. But if you click on the DLVM virtual machine, then you will have a settings button somewhere, either in the menu or right here where it's in my version. And if you go to the settings, and you will see a new window open, and there's likely a systems tab in this window. And in this tab, there are two important settings that we should take a look at for your machine. The first one is the memory slider. In my case, it's in the motherboard tab. I'm not sure if it's always called like that, but there will be a memory slider somewhere that determines how much main memory your virtual machine will get. This is set to 7 GB by default, and that's okay for this tutorial. We don't need to change that. If you want to run larger models inside of the virtual machine, you may want to increase that if your laptop has, or your desktop, or whatever system you're running on, has enough memory to support that. VirtualBox makes that clear usually by coloring the graph below this slider. So as long as you stay in the green area, you can definitely increase this as long up to the maximum limit of the green area. In most cases, you can even increase it a bit further without slowing down the rest of your machine. But as I said, for this tutorial, if you just want to run tutorial models, leaving it somewhere around the 7 GB that the default setting is, that should be fine. The more important setting for today and for the rest of the week is under the processor tab. And under the processor tab, you see how many processors are assigned to the virtual machine. By default, those are 2. And with 2 processors, you will be able to run everything this week, but some things will take quite a while. And many of your systems will actually have more CPUs available. So I imagine that most of you will definitely have 4, but you don't want to assign all 4 to the virtual machine if you have 4 processors available. You want to leave at least 1 for your main operating system. If you have more than 4 available, then it's somewhat of a rule of thumb. So you can, again, you can at least go up to the green bar of VirtualBox. And in most cases, you can actually go higher up, probably up to 2 or 1 below the maximum number that your system supports. So in my case, that would be 10 or 11. But again, that will depend on the system you're on. Feel free to choose a number somewhere between the maximum of the green bar and 1 or 2 below the maximum number of CPUs that you have available. Increasing this number will make things much faster, especially for today and I guess also for the next days. So I will for now stick to 6 processors because I don't need more. But when I run things in parallel inside of the virtual machine, I will still use only 2 processors most of the time for illustration purposes and to know how slow things are if I have a very slow system. But you should feel free to always put in the maximum number of processors that you just assigned. So remember what value you set that slider to, and you can use it today during the lesson to speed things up. I see that we have a lot of chat activity. But it seems that most have been answered. So if you get error messages, then please post the error message in the chat. Otherwise, it's hard to say. If your slider is grayed out and you can't move it, that likely means that your machine is still running. And you need to shut it down before you can change this setting. Okay. Then let's start the virtual machine. And while your virtual machine boots, I will start talking about today's lessons. So today is really still somewhat of a preparation session for the more complex models that we will run tomorrow, Thursday and Friday. But we will also take a look at some details of Aspect's code structure. We will learn about a new feature, the free surface, and we will talk about the differences between build and debug and optimized mode that Timo explained yesterday. So we will start by compiling an optimized Aspect version. Then we will take a look at Aspect's plugin system. We will run a model with a free surface. And then finally, we will modify this model with a free surface beyond what is possible in the parameter file. So we will go a step further than yesterday and think about the question, what happens if I want to run a model and I cannot set a setting in the parameter file that gets me to the model I want. So let's start with creating an optimized Aspect executable. So Aspect executable that is compiled in optimized mode, because we can use that to run models much faster for the rest of this tutorial. I put the instructions to do this on the slide, but I will also do it in my own virtual machine and show you how it's done. So I will switch over to my virtual machine, which has started by now. And I hope it has started for most of you as well. So we will start by opening a terminal, just like we did yesterday, either with the small button in the top bar or by pressing Ctrl-Alt-T. And then we will go into the Aspect directory, which would be cd space Aspect. And then we will create a new directory, which we do with the command mkdir. And then we will call this new directory release. So the command is mkdir space release. If you now check the content of this directory with the command ls, you will see that there's a new directory that's called release. I should mention that if you followed Timo's instructions yesterday already, or have compiled this already, then you obviously don't need to do that. Now let's go inside this new directory, which is the command cd space release. And if we repeat the ls command, we see that this directory is empty at the moment. So this type of directory is called a build directory. We will compile aspect inside of this directory. Now we need to create some instructions for the machine for how to compile aspect. And we do this with the program that is called cmake. So if you type cmake space, and then you need to provide some arguments to cmake. First of all, you would need to provide cmake with a path to deal2, because aspect is built on deal2. Inside of this virtual machine, you don't need to do that because there is an environment variable that is called deal2dir that is already set to the correct path to deal2. So we don't need to provide any argument here. But on a system where this is not set up, you would need to provide a path to deal2, and you would do this by setting this argument. So dash capital D, and then the name of the variable, in this case deal2dir, and then an equal sign, and then the value of this variable. So here would go the path to deal2, whatever that would be on your machine. But as I said, for this virtual machine, we don't need to do that. Instead, we only need to provide a path to the aspect source directory. So in principle, we could create this build directory in any place on the system, but we decided to put the directory inside of the aspect source directory, and so we need to provide it with a path to the source directory, which is exactly one directory above our current one, which is ... in the speech of the terminal. So if we do this, you see that there are some configuration messages appearing. They are of not much interest usually, unless you run into problems later and you want to check what happened during the configuration. And it will take a while depending on your system. And I will use this opportunity to quickly look into the chat because we have lots of chat questions. Is there anything in the chat that we should discuss for everyone? This is a question for my co-organizers.
Maybe Valentina's problem, that the build just stopped halfway through.
That's something. Oh, interesting. Yeah, I didn't realize that you compiled it in release mode in the virtual machine and it crashed at 70%. So the most likely thing, yeah, so we discussed that. Valentina had an interesting problem while compiling in release mode, where it crashed halfway through compiling the release mode with the error message internal compiler error. These types of errors are most often caused if the system does not have enough memory or enough disk space available. That should not happen inside of the virtual machine unless you compiled with a lot of cores at the same time and didn't increase the memory at the same time. So we will see if this happens for me too, but it's relatively rare that this happens. So let's see if other participants run into the same problem, and if so, then we will take a closer look. For now, I think Valentina increased the memory and recompiled, and we will see what happens. So by now, the configuration in my terminal has finished. It gave a lot of output, and one of the lines close to the end says that the CMake build type at the moment is debug. So if we would compile aspect right now, we would compile a debug version of aspect. But we would like to compile an optimized version. So in principle, as always, there are several ways to do this. Timo showed you one yesterday, where you could use the same parameter that we used before, the dash capital D, and then would set the variable CMake build type to release. This is one option. Personally, I find it simpler to just run CMake without this argument, run the configuration for the debug mode, and then afterwards type make space release. So that's what we're going to do now. If you're following along, then just type make space release. And if you do that, then you will see that new configuration messages will appear. The configuration will be much faster. And you should see the first line, or one of the first lines should be switching to release mode. And one of the last lines should be switched to release mode. Now recompile with make. So by running this command, make space release, we told CMake to change the configuration to an optimized or release build of aspect. And now we can start compiling aspect. And we can do this by typing make. And then now comes the part where it's important how many processors your virtual machine has. So compiling aspect takes quite a long time. And that's a feature, or however you want to look at it, it's a property of the C++ programming language, and the fact that we have a lot of dependencies due to Trillinor's P-forest and so on. So we want to compile this on as many processors in parallel as possible. And we do this by adding the parameter -j and then a number. And this number should be the number of processors that you have assigned to the virtual machine. So if you don't have many processors available, and your virtual machine is running with just 2 processors, which is the default, then this would be make space -j2. In my case, I want to make sure that I'm finished with this compiling until we get to the point where we are going to need it. That's why I will run this with -j6, because I have the 6 processors assigned to my virtual machine. Don't worry if you only have 2. It will take a bit more than half an hour. You may not be finished by the time when we are going to use the release mode, but you can use the debug mode instead. And I can use the release mode tomorrow and for the other models that we are going to run later. So it's still useful, even if you are compiling this with only 2 processors, it's still useful to do this and let it finish over the course of the lessons today, so that you can use it for the next days. Actually, thinking about this, I just realized that I left the memory for my virtual machine at 8 GB. And if I would compile this with 6 cores, I would likely run into the same problem that Valentina had, that the memory runs out. So I'm going to limit this to 3 cores for now, and we'll see how long that takes. So with 2, as I said, with 2 cores, it will take approximately half an hour. So when we run this, you will see that first there will be a line scanning dependencies of target aspect, and afterwards it will list the individual files it compiles. That's not very interesting, and we're not going to stick around to look at that. But there's something else that we can do in the meantime. We can open up a new terminal. Let me get the Zoom window out of the way. So we can open up a new terminal, and we can also go into the aspect directory in this new terminal. So cd space aspect. And if you take a look at the contents of that directory with ls, then you will see that there is an aspect binary inside of this directory. Or to be precise, that's not a binary, it's a shortcut, it's a link to the aspect binary that is actually inside of the build directory. So this is the debug version of aspect that we used yesterday. For today and for the next days, we want to have something similar, but for the release version that we are currently compiling. And we can create that with a command that's called ln, probably for link. And we give it 2 arguments, -s and f. And don't worry about the meaning of these arguments for now. And we will link the aspect executable that we are currently compiling, which will be inside of the release directory, and it will have the name aspect. So the second argument to the ln command is release/aspect. And we want to create the link inside of the current folder, inside of the aspect folder. And we want to name it aspect-release. So this is the command that we want to execute: ln space -sf space release/aspect space aspect-release. And when I execute this command and rerun the ls command, you will see that there is a new file in this folder called aspect-release. And you will see that this file does not have the nice blue color of the aspect link that is already in this directory, but it has this broken looking red color. And that's because the aspect binary doesn't actually exist yet. We are currently compiling it in this other window. So at the moment, this link will not work, but it will work once we are done compiling. So this was just some preparation for later. At this point, I want to take a quick break, just 30 seconds or so, to ask if everyone could follow along so far. If you ran into problems, then please post them in the chat, and we will try to figure that out. Some of these things are hard to debug without a lot of back and forth questions, so they may actually be easier to solve in the chat.
I would say, continue, and the rest of us will monitor the chat. And,
okay.
Deal with the questions that come up there.
Good.
So
there
was one question in the chat, which was asking to explain the -sf command.
Oh, sure. So the -f stands for force, and it means that the command will not complain if there is already an aspect-release file in the folder. So it would overwrite that file with the new link. It's not actually necessary in this case, but I put it in there in the case that some of you had already followed Timo's commands yesterday and already created an aspect-release. So with the F command, you will not see an error, but you will just overwrite the file that already exists. And the -s creates a special type of link, which is called a soft link. There's not really much point in going into why we create this type of link than a different one at the moment. So they are not crucial. Okay, so while the optimized aspect binary is still compiling, let's come back to the things we wanted to talk about today. You can leave the compile process running in the background. So just a quick reminder, the reason we are doing this is there are the two modes of aspect, the debug and the optimized mode. And the optimized mode is much faster, but it does not have the error checks that the debug mode has. So just to repeat the points that Timo made yesterday, if you run a new model, always test it in debug mode, because you will get better and more error messages. After you have set up your model, you can run the same model in optimized mode with a higher resolution or for more than one time step if you want to run a time-dependent model. And the optimized mode will save you a lot of time, but the debug mode will also save you a lot of time before that because it helps you set up the model. If you have a crash, if you encounter a crash in optimized mode, then it's a good practice to always try to reproduce that crash in debug mode. Because most likely, if in optimized mode you only see some cryptic messages that are not really descriptive of the problem, in debug mode it's likely that you will see a really useful error message, like your density becomes negative, or some cell gets too much distorted because of mesh deformation. So if you encounter a crash on your cluster with the production model, then try to recreate that crash in a debug mode model, and you will likely get a better error message. And as Timo already said, never run production runs, so big runs that run for a long time in debug mode, because you are essentially wasting your time and whoever paid for the cluster's money. Okay, with that out of the way, let's start talking about our topic for today. We will introduce a new feature today, which is called a free surface. And we will do so by running models in the same folder we were yesterday. So the aspect tutorials folder, 2020 modeling workshop, and then session 2. And I can show you the content of that folder. So I will reuse this terminal that I just created to create the link. And I can clean it up by typing reset, but that's not necessary for you. But so you should already have this aspect tutorials folder and the 2020 Tectonics modeling tutorial directory inside of that folder. And today we will use the directory session 2. So I switch to the directory session 2. And if you take a look inside of that directory, you will see that there are 2 parameter files, freesurface.pim and freesurfacewithcrust.pim, and a plugin directory. And I already have one additional output directory, but you don't need that at the moment. So we are going to talk about surface topography, just quickly, not in detail, but it is useful to point out that there are different ways in geodynamic modeling to model a surface topography. And at least 3 of these ways are currently implemented in Aspect. So first, you could measure the surface topography in a model by calculating the topography that would be created based on the dynamic stress on a fixed boundary. So you can imagine that if you had a model that has a fixed surface boundary and you build up a certain pressure below that boundary, that is higher than the surrounding pressure, then this would push up the surface by a certain amount. And by using the gravity and the density, you can directly calculate how much topography you would build because of this pressure. This is the simplest way to compute surface topography, but it's not very accurate because you neglect every feedback that this topography would have on the solution. So this is a pure post-processing step. The second approach to modeling a free surface is probably one that will be used in the next days as well. It's called a sticky air layer, where you put in a relatively thin layer at the top of your model, and you give this layer the properties of air. Not exactly the properties of air, but it's very thin, so it's very weak, and it has a very low density. And so it's sufficiently similar to air that you can say, okay, the deformation of this layer at the top of the model is approximately what a real free surface landscape would do. But for this tutorial today, I want to talk about the third way, and that is to actually deform the mesh of the model to follow the free surface. So this would essentially, or could look like this. This is obviously not a model that you are likely to run if you want to model a tectonics problem, because it's a model of a sphere, but it illustrates the point of actually deforming the mesh instead of theoretically computing the surface topography or modeling the surface topography by introducing a separate layer and look how this layer deforms over time. So before we talk about how to run this model, let's think about the mathematical properties that this model needs to have to allow for this kind of deformation. What does it actually mean to have a free surface? We often talk about free surfaces to model topography, but what does this, mathematically speaking, mean? First of all, we would need a surface that is stress-free. That's where the term free surface actually comes from. So the velocity boundary condition for the surface has to be stress-free, which means the velocity can simply move through this surface without encountering any resistance. But that's not enough to model a free surface, because if the material would move through this free surface, it would just disappear. The second ingredient that is necessary to actually model surface topography with this approach is a mesh that is deformed according to this velocity that we computed. So the velocity can move through the surface, but the mesh will follow this velocity so that in the end we don't lose material. This approach to model a free surface is called an arbitrary Lagrangian Eulerian approach. In fact, it's not just an approach to model a free surface. The ALE formulation is a general formulation that can be used for other things as well, but we will use it to model a free surface. And these are the two main ingredients that we need to actually deform the mesh. In practice, we will also need a stabilization mechanism for this free surface deformation. And you can imagine why if you think about a very simple solver approach for these two conditions that I described above. So think of a box without any topography, and think of some force that pushes from below against this boundary. What will then happen is you will have some flow through this boundary because the velocity does not have any resistance against the flow. And afterwards, you will move the mesh by exactly this velocity. But of course, in practice, the flow would encounter some resistance as soon as it builds up some topography. So if you just follow the flow, you will actually build up too much topography. And in the next time step, you will likely need to reduce that topography because this additional topography that you created is creating a downward force against this topography. So if you don't have any stabilization, you will essentially build up a mountain. It will immediately collapse. Then you will build up a mountain again. And there, in theory, you can come up with several ways to solve such problems. That's a common thing in numerical mathematics and in computational science to try to stabilize these kind of instabilities. And Aspect has a stabilization mechanism to prevent this. It's based on these two papers that I put on the slide. But we will not discuss in detail the mathematics of this because it's not the main point of today's lesson. I just wanted to mention it here that it's an additional ingredient that we need for the free surface. So let's take a look how you would set up such a model with a free surface. In order to do that, inside of the virtual machine, let's go into this directory, which I already did. And then let's take a look at the freesurface.pim file. So I will use the LeafPad editor for this, but you are free to use the xdg-open that was used yesterday or any other text editor you are comfortable with. I will leave up the instructions for how to get here on the right-hand side. And we will take a look through the parameter file on the left-hand side. So this is one of the cookbooks of Aspect. It's somewhat modified, and the modified version will make it into a future Aspect version. In fact, I opened a pull request for that a few days ago. But let's look through this file at the moment. So documentation essentially states it's a very simple cookbook that will teach us about free surface. And it is a 2D box that has a rising sphere of hot material beneath the surface, which will rise and then spread below the surface, which will generate an initially increasing and then decaying surface topography. Let me see if I can increase the font size. Okay. So the initial parameters that you see up here in the top are very similar to what we discussed yesterday. So I'm not going to talk about them much more. The first interesting parameters are these, the maximum first time step and the maximum relative increase in time step. And this relates to what I just said about the stabilization of a free surface. So free surface models tend to be more unstable than models with fixed boundaries on all sides, and especially in the first time steps, because the first time steps, you can think of this as a time when the free surface has to equilibrate with the pressure and stress in the model. So oftentimes it makes sense to limit the first time step or the first few time steps to prevent oscillations of the free surface. And that's exactly what we are doing here. So we set the maximum first time step length to 1e3, so 1000 years in this model. And we limit the relative increase in this time step. So this is actually in percent. If you look up the documentation of this parameter, it says by how much percent can the next time step increase compared to the previous time step. So in this case, we start with a time step of 1000 years. The second time step can at most be 1300 years. And the one after that can increase further and so on. And that will lead to longer time steps in the end. In practice, there is another control on the time step length in Aspect, which is called the CFL number, which simply scales all time steps that we compute with a certain factor. So we could have just decreased this factor to achieve more or less the same effect as the other ones. But of course, if we decrease all time steps, we will slow down the whole model instead of just the beginning. So that's why I went with the other two parameters for this model setup. The next difference to the models that we discussed before yesterday is this pressure normalization parameter, which is set to no. It's a property of the Stokes equation that the solution is essentially identical if you add a constant pressure to the whole equation, at least as long as all of the properties in the equation are not dependent on pressure. So if your density is incompressible, then you can essentially add a constant pressure everywhere in your model and it will not change the model result. But for free surface models, we want the pressure to be zero at the surface because we have a boundary condition that prescribes a zero pressure or a zero stress, but the pressure is the average of the main diagonal of the stress tensor. So a zero stress implies a zero pressure. So this parameter always has to be set to no for free surface models, and aspect will crash if you set this otherwise. So don't worry too much about it. I will quickly skip over some of the other sections because they are very similar to what we discussed yesterday. There is a small difference in the geometry model section, which are these parameters. I will not discuss them in more detail, just quickly. If you set a certain number of repetitions in a certain direction, then you will get 5 times as many cells in that direction than if you had otherwise. And if you have a box that has a large aspect ratio like this one, then it's a good practice to set the repetitions to the same ratio as the ratio of the extents of the box. The gravity model is just like we had yesterday. It's vertical. The difference, the big difference between a free surface model and the other models starts here in this subsection. The subsection is called mesh deformation. And so you can guess that it describes how the mesh can deform, and that in most models, this section will just be missing and we will not deform the mesh over time. But if you want to have a free surface like we do here, we want to set the mesh deformation. And we set the mesh deformation by setting this parameter, set mesh deformation boundary indicators equals. And then it says top : free surface, which translates to the boundary that is called top will be deformed by the mesh deformation plugin that is called free surface. And you can already see that this is actually independent of the boundary you want to deform. So we could write bottom free surface. That doesn't make much sense, but maybe you will encounter an exotic model at some point where you want to deform a different boundary. Maybe you want to calculate core mental boundary topography. Although there, the free surface is not the correct plugin, but I will not go there in this example. So let's just say we want to deform the top boundary with the free surface plugin. The only other parameter that is set in this subsection is inside of this in the subsection free surface, there is the free surface stabilization theta, which is a parameter that is used in the stabilization for the free surface that I mentioned earlier. This parameter is not very important at this point, but if you want to understand the stabilization mechanism in more detail, then you can take a look in the papers that are linked, and there it is described what this parameter does. In practice, you can most often just leave it at the default value, so I might as well remove this whole section because 0.5 is the default value. But I decided to put it here just to let you know about the existence of this parameter and that you can change it. In practice, you can change this between 0, which means no stabilization at all, and 1, which means the largest amount of stabilization that possibly makes sense. But 1 will likely overly damp the topography of the surface. And 0.5 is the default value. So we'll just leave it at the default value for now. If you remember, I said there are 2 main ingredients for the free surface. The first one was that the velocity can move through the surface. And the second one was that the surface actually deforms and follows this velocity. This subsection describes the second of these conditions. This subsection describes that the surface actually follows the velocity. Now we need to make sure that the velocity can actually move through the surface. And this is done in the boundary velocity model subsection, which makes sense because this subsection describes the boundary conditions for the velocity. But if you take a look inside of the subsection for this model, you will see that there's only one parameter, and this parameter is set tangential velocity boundary indicators. And it is set to left, right, and bottom. So what that means is there is no boundary condition for the top surface, which for aspect translates to the fact we will not apply any velocity or any stress to the top boundary, which is equivalent to the velocity can move through the top boundary without encountering any resistance. So in order to get a free surface, we actually don't have to set anything in this subsection. We have to remove the top boundary indicator from any of the parameters. And that's it. These 2 subsections essentially define that we want to have a free surface in this model. The rest of the parameter file only describes the temperature model, the initial temperature, the material model, and I will not go into very much detail about those because they are relatively easy and relatively similar to the ones we had yesterday. So let's take a quick look. The boundary temperatures are fixed for the left, right, bottom, and top boundary. We use a different plugin than yesterday, but it works very similarly. It's called constant, and it allows a parameter that is called boundary indicator to temperature mappings. So if you take a look at this parameter value, it tells you that we prescribe a temperature of 0 at the left boundary, of 0 at the right boundary, of 0 at the bottom boundary, and of 0 at the top boundary. Very boring. We, just as we did yesterday in the initial temperature model subsection, we use the function plugin to prescribe the initial temperature, the starting temperature. And this looks a bit complicated, but if you look closely, it is just the formula for a sphere. So it essentially prescribes the temperature to be 200 inside of a sphere and 0 outside of a sphere. And the material model we are going to use is called simpler, which is actually at the moment the simplest material model that we have in Aspect. And we will take a look into that later, but we don't need to worry about it for now. We will prescribe a certain mesh refinement, and we will again only use global refinement. We will not go into Aspect's capabilities for adaptive refinement right now. And in terms of post-processors, we use the post-processors that are called visualization to output ParaView output, velocity statistics, which will give us the average and maximum velocity at each time step, and topography, which will output the maximum and minimum topography at each time step. And we are going to use that. So this is the type of model we want to work with today. I'm going to close this. As you can see, my compilation process in the other window has just finished. It's possible that yours will still take a while, so we'll wait for that for a bit. And at this point, we're going to take a quick break of maybe 10 minutes or so. Before we go into the break, are there any questions that we should discuss right now for everyone?
Rene, there were some questions about how things are converted from years to seconds internally in the code, if that option is selected in the parameter file.
Yeah. So let's reopen.
Right, I guess the question was also about how then the equations are solved internally.
Okay, yep. So that was quick, like that was mentioned in passing yesterday, but it's worth pointing out again because it's an important point that comes up again and again because it's a bit confusing. So the most important parameter for you when you write an input file is actually this global parameter, which says use years in output instead of seconds. If you use this parameter, if it's set to true, then you can assume that any input parameter in the parameter file that has to do with time is expressed in years. So the end time in this case is 2e7, so 20 million years. Internally, Aspect will, if this parameter is set, will convert this into seconds. And will assume that everything is in an MKS system, so in meter kilogram seconds, or SI system. That's the simple answer. I can make this a bit more complicated to make a bit more the point of what actually happens. Aspect does not really care which unit system you use, as long as all of the inputs are in the same unit system. So if you would non-dimensionalize everything of this, all of the input parameter, then Aspect would work just as well. It would just compute everything internally in the non-dimensionalized unit system. But by default, we decide to put in all of the parameters in SI units because it's more intuitive and it removes the necessity to non-dimensionalize everything and removes all of the possibilities of how to wrongly non-dimensionalize things. But Aspect internally doesn't really have a notion of which units it's computing in. The only exception is this parameter, which makes it possible for you to put in everything in years instead of seconds. Does this more or less answer the questions? All right, yeah. So if all of your other parameters are in meter kilogram seconds, then of course your temperature is in Kelvin. Yes. And yeah, the question about the compilation error with make, that has likely something to do with which directory you are in and if you run the cmake command before that. Yeah.
We'll try to figure this out in the chat.
Okay. So then I would say we take a 10-minute break and come back afterwards to talk about how to modify this model and take a look at the results. If your compile process has already finished for the release mode, then feel free to actually run this model over the break. So to go into this directory and to execute this command inside of the directory. We will not take a very close look at this model. We will actually care about the other model in that directory more. But if you have already finished, then feel free to use that. So with that, I would say we'll take the 10-minute break and meet again at 15 past the hour in most time zones and 45 past the hour in India. And I will leave up this slide during the break.